Today we're going to talk about the deBroglie-Bohm interpretation. So let me kind of remind you of the big picture. On the very first day, we talked about the orthodox interpretation of quantum theory and what its deficiencies were. And we identified a whole bunch of ways in which you could try to do better and obtain a realist interpretation of the formalism. So last week, we looked at what realist interpretations that invoke hidden variables might look like. And in particular, we talked about the distinction between psiontic and psi-epistemic hidden variable models. And we saw some hidden variable models that could reproduce parts of quantum theory, wherein the quantum states were epistemic. So non-orthogonal quantum states were represented by overlapping distributions in the hidden variable space. And then we saw how Bell's theorem and the quotient-spector theorem implied that any one of these realist interpretations had to have non-locality in it, had to have contextuality in it. And that was true regardless of which sort of approach you took. So today we're going to see a more traditional kind of interpretation where the quantum state is ontic, which means that although it's going to be supplemented by some extra hidden variables, so that the full description of reality is not just the quantum state, it's still true that the quantum state is part of the description of reality. OK. So here's the basic idea. So I'm going to start by telling you what the deBroglie-Bohm interpretation looks like for just a single particle. And later we'll generalize to multi-particle systems. So the ontic state, which is the complete description of the reality that this theory postulates, consists of two parts. The first part's just the wave function over space for that particle. And the second is some explicit particle position, which I'm going to denote by zeta. So it's a vector in whatever dimension of space you're considering. And it's sometimes called the Bohmian position. So the idea is that in addition to this, in space, in addition to the wave function, you've got a point in the space that specifies the actual position of the particle. And you have some dynamics for both of those. So the dynamics for the wave function is just given by the Schrödinger equation. Okay, so nothing has changed about the wave function. It evolves in exactly the way that orthodox quantum mechanics would predict. And the evolution equation for the Bohmian position is given by this equation. So S here is the phase of the wave function. So what you're asked to do is take the wave function, decompose it in a polar decomposition. So capital R denotes the modulus of the wave function. And S over H bar is the phase in the position representation. So you're asked to take the phase and take the gradient of the phase and evaluate that at the position of the Bohmian particle. That will tell you the velocity of the Bohmian particle. And so using these two equations, you can evolve both the Bohmian position and the wave function forward in time. This equation, incidentally, is often called the guidance equation. That's how I'm going to refer to it. So that's the basic idea. So a couple of things to note about these guys. Although it looks like a wave interacting with a particle, and that sort of thing appears elsewhere in physics, there's an important difference here, which is that although the particular state of the wave function does influence how the particle moves through the guidance equation, you'll notice that the actual Bohmian position of the particle does not influence the wave function at all. So the Schrödinger equation dictates the evolution of the wave function, and it's independent of this position. So there's an action from the wave function to the Bohmian position, but no back action. And that's unlike most field theories. The second thing you might notice is that this guidance equation for the Bohmian position doesn't depend at all on the amplitude of the wave function. It depends only on the phase. And so if I change the amplitude in some region without changing the phase profile, that won't affect the velocity of the particles or how they move. And so that fact about the dynamics has led people to call the role of the wave function in guiding the particle a sort of pilot wave role. So the following analogy describes it well. This is due to Bohm if the captain of a ship receives a radio signal about where to steer, it doesn't matter what the amplitude of the radio signal is as long as it's received. It's the information that's encoded in that signal that dictates where the ship moves to. And similarly here, it's the form of the wave function encoded in the phase dependence that dictates how the particle moves and not the strength of the signals. Okay, so if you decompose the wave function in position representation in the polar decomposition, and you re-express the Schrodinger equation in terms of its real part and imaginary part in terms of those R and S degrees of freedom, this is what you find. So I'm not going to do the derivation here. You may see it in your homework this week. So the real part ends up looking like this. So S, again, is the phase. So this equation holds for S, where Q is given by this formula. So V is the external potential. M is the mass. Q is given by this formula, which is called the quantum potential. So it appears to play the same role as the external potential does, but Q depends on the form of the wave function. So remember that R is the modulus of the wave function. And this here doesn't depend at all on, again, the magnitude of R, because if I multiplied R by some scalar, it would cancel in this equation. So again, the quantum potential depends on the form of the wave function, not on its intensity at a given point. Does this equation look familiar to anybody? So it turns out there's a strong analogy between dynamics in the deBroglie-Bohm interpretation and the Hamilton-Jacobi approach to classical dynamics. So this is the Hamilton, if this were just an external potential, so if this term were in here, then this is exactly the Hamilton-Jacobi equation where S is Hamilton's principal function. I'm not going to dwell on that analogy, but a lot of discussions of the deBroglie-Bohm interpretation see it as a kind of generalization of the Hamilton-Jacobi formulation of classical physics. And that gives a nice language by which to compare classical physics to quantum physics according to this interpretation. The imaginary part of the Schrodinger equation ends up looking like this. And this is basically an equation that describes the conservation of probability. So R squared is just the modulus of psi squared by definition. And so this tells me how much probability changes at a particular point in space. And this describes the amount of probability that's leaving that area of space. Because this is like the velocity term. Well, if you look in sort of undergraduate textbooks on quantum theory and you look to the place where they talk about the probability current defined by quantum theory, you'll find this sort of equation. So we'll come back to that and see how it's relevant to the probability distribution over Bohmian positions. Good. So using this new form, this quantum potential, there's another way of expressing the dynamics than the one I showed you on the first slide. So I can take another derivative with respect to time of the Bohmian particle position. So the guidance equation gave it the velocity. I can calculate the acceleration. And what I find is something of this form. So it looks just like Newton's law, where the gradient of the external potential would specify the force that determines the acceleration of the Bohmian particle. But you have this extra kind of potential term, which I showed you on the last slide, which is called the quantum potential. Of course, and you evaluate this at the particular Bohmian position. So as I mentioned before, that this thing does not depend on the strength of the field, but it will imply forces on the particle. So even if the external potential V is 0 everywhere in some region of space, so that classically Newtonian mechanics would tell us that there's no accelerations and the particles are going to move rectilinearly with constant velocity. In the deBroglie-Bohm interpretation, you have to look at the wave function. And even though the external potential is 0, the wave function might have some interesting structure, which would define a non-trivial quantum potential, which will imply forces on the particles. So the particles could be accelerating, changing direction even though there's no external potential in this theory. And we're going to see some examples of that. Okay. I don't think I'm going to go through this. This is the proof of that Newtonian form of the deBroglie-Bohm interpretation. So you can just take the real and the real part of the Schrodinger equation, act the gradient on it, you get this equation. And so then when you take the derivative of the guidance equation, you see that this term here can be replaced by this gradient. And so you get the equation I showed you. So now the question is, well, actually, no. Let me tell you some more facts about the Newtonian approach a little bit later. Well, this is just a summary of what the Newtonian form looks like again. And the question is, in addition to this potential term, which we don't see classically, how does this sort of dynamics, the dynamics implied by Bohmian theory, differ from the classical dynamics? So there's another important respect in which it's different that's kind of obfuscated by this way of presenting it. I'm just wondering if anyone sees what it might be. Exactly. Exactly, yes. So in Newtonian mechanics, your boundary conditions require you to, because it's fundamentally a second-order equation, you have to specify the positions and the velocities, and they're independently specifiable. But in the deBroglie-Bohm interpretation, once you specify the position of the particle and the wave function, then the velocities of the particle are completely determined. So you don't have freedom to specify those. And for that reason, many argue that it's better to present the theory in this form, where it's clearly a first-order theory, than in the Newtonian form. Yes? Yep. No, because as we're going to see, when you ask what gets revealed in a measurement, and so you say, suppose I do a measurement of the position observable, do I discover the Bohmian position? And when I do a measurement of the momentum observable, do I discover the mass times the Bohmian velocity? For some cases, the answer is yes, but in general, the answer is no. So typically, the result of a measurement depends not just on the, say, Bohmian velocity, but on the wave function as well. And therefore, the measurement statistics respect the uncertainty principle. And in fact, what I'm going to prove to you is that this interpretation is going to make all the same predictions as usual operational quantum theory. Other questions? So the fact that it's a first-order theory means that the kind of dynamics that's postulated here is extremely different from the Newtonian theory. So in Newtonian mechanics, it's accelerations that need to be explained. And why something maintains its velocity is not something that requires explanation. Whereas in the Aristotelian model of physics, which came before Newton, people thought they needed explanations for why something doesn't, say, come to rest. So they were looking for explanations of the velocities of the particles, not the accelerations. And in this sort of model, it's more Aristotelian than it is Newtonian. You have an explanation for the velocities of all the particles that involves appealing to their positions and the wave function and the guidance equation. Okay, good. So if you ask, what do you know about the Bohmian positions when you have a description of the wave function? So suppose you've done operationally a preparation procedure, you know the pure quantum state, and you ask, well, what does Bohmian mechanics tell me I should say about those Bohmian positions? So it presumes that the probability that the particle is within d zeta of position zeta, which I'll just denote, I'll denote the probability density rho zeta, is just given by psi squared. So this is an assumption. For now, we're going to treat this as an assumption of the interpretation. And it's called the standard distribution of the Bohmian particles. And what's interesting about making this assumption is that once you've made it at one time, it must hold at all times. Okay, so if I start off at time 0 with a probability distribution of the Bohmian positions that corresponds to psi squared, then at every other time it's going to be psi squared. Let me show you the proof of that. So the guidance equation will define a velocity field over all space through the gradient of the phase. And therefore, I can define a probability current density just using whatever the probability distribution of the Bohmian particles are. So for the moment, let me not assume that it's necessarily psi squared. It's anything. No matter what rho is, I can multiply it by the velocity field and get a probability current density over the space. And then the formula for conservation of probability tells me that the rate of change of the density in any region is going to be given by the gradient of that probability current. But I know, I can just plug in the formula for the probability current, and I've used the formula for the velocity field in terms of the gradient of the phase. And now I ask you to remember that imaginary part of the Schrodinger equation expressed in terms of psi squared, right? So remember, r squared is just mod of psi squared here. S is the phase. So now these two facts allow me to show that if initially rho is r squared, then it's always r squared. Because if at some time rho is equal to r squared, then I can calculate, by just taking the difference of these two equations, I can ask what's the rate of change of the deviation of rho from r squared. So I want to know rho minus r squared, how does that change over time? Does it depart from being everywhere 0? Well, if I look at the difference of the right-hand sides of these equations, I have a rho minus r squared here. That's everywhere 0. So the right-hand sides are 0. So it says that this is not going to change at all. And so it's going to be preserved in this form at all times. Yes? Yes. So maybe at the end of this lecture or the beginning of the next lecture, I'll talk about ideas people have had for deviating from this assumption. And what would imply if the distribution of the Bohm particles was not given by psi squared. And what you can show is that although in certain circumstances you can approximate the quantum predictions well, you also predict some deviations from the quantum predictions. And that's something that you could experimentally test and compare with quantum theory. So you really do get different predictions if you make a different assumption. And I should say that that's a nice example of the fact that your interpretation can be relevant to experiments because a given interpretational strategy will often lead you to develop your theory in a particular way that will make certain experimental predictions that deviate from the orthodox point of view. So we're going to see an example of that with these non-standard distributions. OK. Let's look at a simple example of what the Bohmian theory predicts. So consider a 1s orbital of the hydrogen atom, and consider the wave function. Well, mod psi squared is going to be some sort of whatever the profile of the 1s orbital looks like. And the important thing is that it's actually a real wave function. It's not complex at all. So if I look at its evolution over time, it will pick up this global phase factor here, but that phase factor has no spatial dependence. And therefore, if I look at the gradient of that phase factor, I find it's just 0 everywhere. So that tells me that the velocity of the Bohmian particle is 0. So when I know that the wave function is psi, I know that the Bohmian position is drawn somewhere from this distribution. It's more likely to be near the center than it is at the fringes. And then the guidance equation tells me the way it moves is to just stay put. It just it doesn't orbit around the nucleus. It just sits in space at a fixed distance from the nucleus. So that's a very odd way for the model to come out, but it's what the guidance equation predicts in the deBroglie-Bohm interpretation. All right, so now to tell you a couple more facts about this theory, I'm going to need to tell you about occupied and empty waves. So imagine you have a wave function that's written as a sum of terms, a sum of psi j's. And suppose that the Bohmian position lies in the spatial support of psi j. So what I mean by the spatial support, I guess I should draw this, is that region of space which is assigned an amplitude significantly different from 0. So if I have some wave function like this, then the spatial support will be that region where this wave function differs appreciably from 0. So this would be just a one-dimensional space, but it's the same with any dimension of space. So if the Bohmian position lies inside the support of psi j, then we'll say the jth wave is occupied. And if the Bohmian position for some psi j does not lie inside spatial support, then that wave we'll say is empty. Question? Yes? Well, there will be a distinction between things like the position you find as the outcome of a measurement on the particle and what I'm calling the Bohmian position. But I think proponents of this interpretation will say, when we talk about the position of an object, well, in the orthodox approach, that's sort of illegal. We can only talk about the position of an object if it's in a position eigenstate. Whereas in the Bohmian approach, it's always appropriate to talk about the position of object. It has a well-defined position, and it's given by the Bohmian position. And it doesn't evolve in the way that classical position would, but that's the innovation of quantum theory. And what we're also going to see is that the position of the particle is going to settle issues having to do with Schrodinger cats and the measurement problem by picking out a branch of the wave function and saying, the cat really is alive because the positions of the particles inside the cat are inside the wave corresponding to the cat being alive. And the branch of the wave function corresponding to the cat being dead, that's the empty wave. And so this distinction between occupied and empty is actually going to serve to pick out particular branches of the wave function as being the ones that describe what we see. Yeah.
So this composition of the psi in terms of psi j, out of psi j is not decomposition any basis for the space we're interested in, any basis to choose?
So typically this is, people talk about this when they've chosen some orthonormal basis for the space. So the psi j's can be an orthonormal basis, and then we can talk about whether any given term is occupied or empty. Yeah.
So if I choose the basis other than the position basis, but zeta represents the Bohmian position, then how can the Bohmian position be in the spatial support for a non-position psi j?
Because it's not just the position eigenstates that can be drawn as a wave function. So for any wave function, so it could be an eigenstate of position, momentum, any observable you like. Say you drew, say, the 17th excited state of a harmonic oscillator potential. Well, it's going to have some region where that wave function is appreciably different from 0, and the rest it's going to be close to 0. And so it's just the region where it's appreciably different from 0 that I describe as the spatial support of that wave function. So you'll see why this is a relevant distinction soon. OK, so if only one of these waves is occupied and all the others are empty, so let's suppose it's the kth wave that's occupied, then it turns out that the guidance equation, or I should say, the way the particle moves, is now going to depend only on the form of that kth wave and not at all on any of the other terms. So let me convince you of that with a simple example. So another way to say this is that I'm going to show that the empty waves are ineffective in the sense that they don't govern the dynamics of the particle at all. So suppose I just have some wave function that's written as a sum of two terms, psi a and psi b. And here, they don't necessarily have to be with equal coefficients. I'm just going to absorb the coefficient into the definition of psi a so that these wave functions aren't normalized. Then I can write if I write all of these in the polar decomposition, so R is the modulus of psi, S is the phase of psi, and so on for psi a and psi b. Then if I want to know how particles move, I have to look at the gradient of S. And if I want to look at the quantum potential, I have to find R squared. So if I express r squared in terms of RA, SA, RB, and SB, then it has this sort of form. And if I express the gradient of S, it has this ugly-looking equation here. I'm not going to derive either one of those for you, but you can take my word for it. This is what you get if you work it out. And now assume that psi A and psi B are such that they have different non-overlapping spatial supports. So RA, which is the modulus of psi A, times RB, gives me approximately 0 everywhere in space. And then furthermore, I'm going to imagine that also the gradient of RB is close to 0 wherever RA is appreciable. So not only is RB close to 0 wherever RA is appreciable, I'm also going to imagine that it's smooth in that region. And similarly with A and B reversed. OK, so that's often typical of wave packets that are separated. And so in that case, this formula for r squared reduces to just RA squared plus RB squared, because this term goes to 0. And the formula for the gradient of S, well, this term is going to go to 0 because of RA, RB. And each of these is approximately 0. So grad of S is going to be approximately given by this formula. So that will tell me how the particle is going to move. So let me just remind you of the guidance equation. So the velocity of the Bohmian particle is just given by the gradient of S evaluated at the position of the Bohmian particle. And so now imagine that the position of the Bohmian particle is in the spatial support of, say, psi A. It can't be in the spatial support of both because their spatial supports are non-overlapping. So imagine it's in the support of psi A. That's this case. Well, if I look at this formula, I'm supposed to evaluate the grad of S at that position. But RB is close to 0 at that position. So this term goes away. This term goes away. The RA squareds cancel, and I just get the grad of S is grad of SA. So the velocity of the Bohmian particle is entirely determined by the phase of the psi A component when the Bohmian particle is in the support of psi A. And of course, if the Bohmian particle were in the support of psi B, then the same sort of calculation tells me that its dynamics is totally governed by the phase of the second component. So that's what I mean by the empty waves are ineffective. If psi A is occupied and psi B is empty, well, then the dynamics of the particle doesn't depend on the form of psi B at all. Is that clear? All right. Let's look at some more examples of Bohmian trajectories. So this is the paradigm example that you'll find in all the textbooks on Bohmian mechanics. It's the double slit experiment. This is from a very old paper by Dudney and al. And so they basically just looked at a situation where you had a pair of slits, a single particle, and this is the region beyond the slits. So they imagined an initial condition for the wave function, which was basically a Gaussian distribution with equal amplitude coming through these two slits. And they evolved that wave function forward, just using standard quantum mechanics, figured out what the wave function looked in this region. And then they started out with the initial condition of the Bohmian particle, just drawn at random from these two Gaussian distributions, and evolved that forward according to the guidance equation. And then what's drawn here is just a representative sample of those different trajectories. So it represents what the trajectory is for many different initial positions of that Bohmian particle. And so what you see, first of all, is that these trajectories are kind of wiggling through space. And that's a nice example of the fact that even though there's zero potential in this region beyond the slits, nonetheless, the Bohmian particles aren't moving rectilinearly. They're accelerating and moving along these curved lines. If you look at, in the far field, it looks like an interference pattern. Of course, we know that has to be the case because I proved to you that if you start in the standard distribution, so if your Bohmian positions are distributed according to psi squared here, then they'll be distributed according to psi squared here. And psi squared here has the interference pattern. So I expect to see nodes in this, in my probability of, the probability that the deBroglie-Bohm interpretation assigns to the particle being in one of those positions. Also, prior to the point where these guys have interfered, right, this wave packet and this wave packet, times earlier than this, they haven't encountered one another. And in those times, the Bohmian position is in one of these two waves. Let's say it's over here. So then this wave is occupied and this wave is empty. And in that case, the velocity of this guy is determined only by the wave packet corresponding to a Gaussian over here. And if you look at that, it's just a dispersing wave packet. And the evolution it dictates for the Bohmian particle is just rectilinear evolution with some velocity. And it's only when these two wave packets start to interfere, right? So, this, say, region of space here, the two wave packets are now interfering. And any Bohmian position that lands the particle over here, well, now it's starting to see, it has both of those branches of the wave function being occupied. And so now the dynamics doesn't depend on just one branch of the wave function. It depends on both. And that's where you start seeing this interesting dynamics that isn't just dispersion. It's not just half of the wave function spreading out. And so people sometimes describe the motion of the Bohmian particle in this sort of experiment as there's a wave and a particle, right? So the ontology says the wave function's real. The particle position's also real. And the particle position is sort of surfing on this wave, and how it moves depends on the particular form of the wave. And so that's how these guys resolve wave-particle duality. They say, yeah, there's both, and the particle position is guided by the wave. What else can I tell you? I should mention that, let's go back a bit. You might have been concerned about a couple of things. Let's go all the way back. What about the fact that if I look at here, at the Bohmian potential, well, if R is 0 at some point in space, then it would seem that this is not well defined. Similarly, if I go back to my guidance equation here, at those positions where R is 0, the phase also isn't well defined. So how is the theory meaningful, given that we have this problem of phase and the quantum potential sometimes being undefined? Yes? Exactly. So as long as you're in the standard distribution, which says that the probability that the Bohmian position is at one of these nodes of the wave function is 0, then you'll always stay in the standard distribution, and you'll never evolve into one of the regions, one of the nodes of the wave function either. So the very points where the dynamics is not defined are points where the particles always have probability 0 of being found. And so in particular, those nodes in the interference pattern are points where the dynamics would not be well defined, but fortunately, we never find the particles there. All right, here's another example of Bohmian dynamics. So this is just evolution through a potential barrier. So if I did if I solved the Schrödinger equation, the assumption here is that the initial wave packet is just a Gaussian, comes in with some velocity. Part of that is transmitted, part of it's reflected. And then again, what's been done here is just a representative sample of the Bohmian trajectories and how they evolve. And what you'll notice is that, so in this case, it's the probability of transmission is a half. It's exactly the front end, the Bohmian trajectories that are in the leading edge of this Gaussian wave packet that are transmitted, and the ones that are in the trailing one are reflected. Here's another example of this sort of thing. This is basically a beam splitter where one particle, which is in a superposition of a Gaussian wave packet here and here, are being impinged upon this beam splitter. And this is the wave functions then get reflected and transmitted. And again, you find for all the possible Bohmian trajectories, the ones from the bottom all get reflected, and the ones from the top all get reflected in the case where this is a 50-50 beam splitter. So there's a striking pattern here. In addition to the fact that it's not Newtonian in the sense of not being rectilinear, there's something about these sorts of trajectories that you wouldn't see for Newtonian trajectories. Yes, Tom? You're asking why is it that they never cross? Yeah. Good. Yeah, so what I was trying to draw from you was the fact that they never cross. I mean, that's very striking. So here, the reason all the ones in the leading edge have to go through and all the ones in the trailing edge have to be reflected is that they never cross. There's a principle in the deBroglie-Bohm interpretation that tells you trajectories never cross. And all these patterns have that feature. And the question, as you say, is why? So does anyone want to volunteer an explanation of that? Yes?
Because of the first order nature of the balance equation. So at any particular position, the velocities will be different. So you cannot really specify both the observation and velocity.
Exactly, yeah. So in a Newtonian theory, trajectories can cross because it's possible for a particle to be in a given position and have any velocity. Whereas in this theory, if you specify the position the particle's at, then it has to move with a particular velocity from that point on. And so there's no way I could have two crossing trajectories. All right. Any other questions about the single particle case? Yes?
I wonder why it's the trajectories that meet the barrier first that make it through.
Well, if trajectories could cross, then I could have some of these trailing edge guys cross over some of these inner trajectories and get through. But if I'm telling you that the trajectories cannot cross, so I'm imagining this is all dynamics in a two-dimensional plane, and I know that some of the input trajectories have to come out on top and some have to come out on the bottom, well, the only way I can do that is if, without crossing them, is if all the trailing edge come out on the bottom. Yep. Well, like we were just saying, the principle that, so I'm inferring this from the no crossing of trajectories. And then you say, well, why no crossing of trajectories? Answer, because the dynamics is first order. So at every given position, there's a unique velocity. So that's I didn't even need to appeal to the particular form of the dynamical equation. All I need to tell you is that it's a first order equation. That's enough. It follows that the trajectories can't cross, and that implies that it's only the leading trajectories that could possibly get through.
Usually, I was thinking progress through possible progress through a barrier.
Mm-hmm.
I think of something as getting through that barrier that has enough energy and being reflected if it has too little energy.
Okay.
It's a similar story relative.
Well, you could certainly sort of look at the equations of motion for this particle in this situation. So the way it would look is, this potential barrier would imply a very specific kind of wave function evolution. And then that wave function evolution would define exactly what the guidance equation for each of these particles is. Equivalently, I could say that that wave function evolution defines what the quantum potential looks like. And the quantum potential, together with this potential, tell me what the sort of Newtonian form of the equations of motion for this particle looks like. And then I could do just a numerical simulation like these guys have done to see how those particles move. And you get this sort of result. So it's, in terms of, can I just say that it's the ones that have high energy that make it through the barrier and those with low energy don't? I mean, offhand, I haven't looked at this, but it seems like the answer is no. It's not merely a feature of the energy of these Bohmian particles, but it's a complicated function of both the nature of the wave function and where the particle started out. So it's not as simple as in the classical case. I think it does, yeah. That you could think of these trajectories as being a result of the particular form of the quantum potential. So it will specifically sort of prevent any of these trajectories from making it through and allow these trajectories to get through. But I guess what I was arguing earlier is that I don't need to work out the particular form of the quantum potential to conclude that. This no crossing of trajectories principle is already enough. Yes?
So for the beam that comes in,
Yep.
I mean, so how is the velocity transition? I mean, I'm just curious. There has to be symmetric fit, or
How does... So if I look at this wave function, suppose I've chosen it to be a wave packet with some mean momentum. Well, it's going to disperse slightly, which is going to change its position distribution. But let's not worry too much about that. Let's say it's dispersing slowly. So it has some mean momentum, and that momentum is encoded in the phase factor in quantum mechanics. So it's like an e to the IPx term. So then when I look at the gradient of that phase with respect to space, I get p. So it basically tells me that the momentum, the Bohmian momentum, the Bohmian velocity times the mass, is just going to be the momentum of the wave packet I've prepared. So all these guys are moving at the momentum that's specified by that wave packet. And it's only when you get here and all of a sudden the wave packet starts doing something much more complicated that you get, there's these wiggles in the Bohmian positions. And that's the places where the incoming wave packet and the reflected wave packet are interfering and giving me some more interesting phase dependence. Yes? Yes. Yeah, that's right. Okay, let's look at the same theory, but now for more than a single particle, for many particles. And I'm just going to do for 2 particles because it's easiest, but it generalizes. So now if you ask, well, what is the ontic state for a pair of particles according to this theory? The answer is the wave function for the pair of particles. So that's now a wave function on configuration space. So R1, let's imagine that the space we're thinking about is a 2-dimensional space rather than a 3-dimensional space, just because it's a little bit easier to visualize. So R1 is a vector in a 2-dimensional space. R2 is a vector in that 2-dimensional space. The whole configuration space of this pair of particles is now a 4-dimensional space, and the wave function is defined on that. And then in addition to the wave function, there's 2 particle positions, one for the first guy, one for the second guy. I'll denote them by zeta1, zeta2. And they're points in the real 2-dimensional physical space. Okay, if you look at the evolution equation, it's just Schrodinger's equation again for the wave function. But now it's Schrodinger equation for 2 particles. And if I look at the guidance equation in this case, it's given as follows. The velocity of the Bohmian position of the first particle is given by the gradient with respect to the first particle's position of the total phase factor for the wave function. So I write the wave function in the configuration representation. I decompose it in its polar decomposition. That's what S represents here. And then I evaluate that gradient at the Bohmian positions of particle 1 and 2. So we see that there's the velocity of Bohmian position, the Bohmian position of particle 1 can depend on where the Bohmian position of particle 2 through this equation. And similarly here, we have a symmetric equation for the Bohmian position of particle 2. It can depend on the position of particle 1. The fact that this wave function is on configuration space rather than real space is going to make a big difference in how we can potentially interpret it. So I can't, in general, think of, if I'm looking at a 2-particle problem, I can't really say that these 2 particles are essentially being guided by some wave through space, because the wave that's guiding them is no longer a physical space wave. So it's not like surfing on a water wave any longer, because this thing doesn't live in this space. It's still going to be guiding those guys, but it's part of the ontology of this model involves a wave that lives in a very different space, not physical space. Okay. So now let's talk a bit about the details of this dynamics. And I'll start with a simple case where the wave function is just a product state. So if I write each of the components of the product in their polar decompositions, it looks like this. And therefore, the total phase of the wave function is just the sum of the phases of the 2 factors in the product. So it means that if I work out the velocity of the first Bohmian particle when the wave function is this product state, it asks me to just take the gradient with respect to R1 of the total phase factor. But in this case, this guy here doesn't depend on R1 at all. So that's just the gradient of S1. And I can evaluate it at just the position of the first Bohmian particle. And so for this product state, in this special case, the position of the first Bohmian particle doesn't depend on the position of the second Bohmian particle at all. And of course, similarly for the second particle, it depends only on the phase of its wave function and not at all on the wave function or the position of the other particle. So basically, the two particles are going to evolve totally independently if their wave function is a product state. If their wave function is an entangled state, then no surprise, things are going to be different. So suppose that it's the jth wave out of all these terms. So here I've written the wave function in the bi-orthogonal or Schmidt decomposition. So the phi j's and the chi j's are orthonormal bases for each of these spaces. And now suppose that the actual Bohmian positions of particles 1 and 2 make the, or, well, first let me just define it. If I have this sort of situation, then I'll say the jth wave is occupied if the Bohmian positions lie in the support of that guy. And if the Bohmian positions don't lie in the support of one of these terms, then I'll say that that wave is empty. So it's the same definition we had before, but just now for basically it's whether the Bohmian configuration lies in the configuration space support of that term of the total wave function. Okay, so now imagine that only one of these waves is occupied and all the others are empty. So suppose it's the kth wave. Well, in that case, the particles will again evolve independently. Because if the kth wave in this term is the occupied wave, then, from what we saw earlier, only the occupied wave determines the dynamics. But in this case, the occupied wave is a product state. And what we just saw was that the product state tells me that each particle is going to evolve independently. So when one of these waves is occupied, the particles will evolve independently. However, in general, that doesn't happen. If I have more than one of these waves occupied, that's when the particles start evolving in manners that depend on the wave function and the position of the other particle. All right, so let's look at an explicit example of that. So I'm going to imagine two particles. The first one you can think of as it's a particle that's confined to a harmonic potential well. Chi A and chi B are the first excited and the ground state and the first excited state of that potential well. And I'm going to imagine that the second particle is in one of two wave functions, phi A or phi B, that are just localized wave packets that are moving off at some constant velocity. And phi A is going to have a larger velocity than phi B. And now I'm going to imagine that the overall wave function is this entangled state here. So, the phi A wave function for particle 1 is correlated with the chi A wave function for particle 2, phi B with chi B. And if you think of the ground state as being the low energy and the excited state as the high energy state, the high velocity is the high energy and this is the low energy state, you can imagine that this sort of wave function could have arisen by an energy conserving interaction, where if this guy is excited, then that guy moves off slowly. If this guy's ground state, he moves off quickly. And the question is, well, what are the dynamics of each of these particles going to look like, the Bohmian positions of these particles, under this sort of wave function? All right, so first of all, notice that these two waves have disjoint support on the configuration space, because phi A and phi B have disjoint support, right? If I multiply phi A and phi B, I get essentially 0 everywhere. And therefore, if I multiply this product with this product, well, it's enough for phi A and phi B to multiply to 0 for the whole product of this and this to multiply to 0. So it actually doesn't matter that these guys have overlapping support. This wave and this wave are still disjoint by virtue of the disjointness of these guys. So only one of these waves can be occupied, and the other one must be empty for any Bohmian configuration of the particles. So let's select a Bohmian configuration from those in the standard distribution, and let's select ones that are assigned, high probability according to that distribution. So it could be that the first particle is near the center of this green wave, and the second particle is, say, here in the potential well. So in this case, this is the occupied wave here, because that Bohmian position makes phi of zeta 1 evaluate to 0. So this is the occupied wave. So it's the one that's going to govern the dynamics. Now, because it's a product state, it says that these two guys are evolving totally independently. So for example, particle 2 is the general guidance equation. But in fact, it reduces for product state to just the gradient of S2 evaluated at the Bohmian position of zeta 2. So it basically is just entirely governed by chi A, the ground state of this harmonic potential. That's a state that has that's totally real. So the gradient of the phase for that guy is just 0. So the particle just stays put. It doesn't move at all. So if this is time and this is position, then this blue line here denotes the trajectory of that particle. And I've just drawn here the overall standard distribution for particle 2, which is just the sum of psi squared for each of these guys. And CA and CB have been chosen to be 1 over root 2 in this case. OK, so far, nothing interesting is going on. Bohmian position 2 is just staying put. Now, imagine that somewhere over here, I put a mirror in the path of this particle to reflect the wave function back. Well, if I do that, then there comes a point in time where this wave function starts to overlap with the other wave packet for this particle. And when that happens, all of a sudden, the Bohmian configuration, zeta 1, zeta 2, now lies in the support on configuration space of both these wave packets. Right? So you see here, now it lies inside the support of the red and the green. And this guy always was lying inside the support of both the red and the green guys. So now both of these waves are occupied. And so that the dynamics is going to be governed by the overall phase of this wave function and can't be reduced to the phase of just one of these terms. And so the consequence is that all of a sudden, this Bohmian particle here starts evolving differently by virtue of the difference of its dynamical equation. And it sort of registers the fact that over here, these wave packets have re-interfered. So I can imagine that this is happening extremely far away from this at space-like separation. Right? So maybe this is light years away from this. And nonetheless, this Bohmian position of particle 2 will start to change in response to whether this mirror was put here or not. If the mirror doesn't get put in, this Bohmian position continues as it was. If the mirror does get put in, the Bohmian position responds. And so clearly, we have a failure of Bell's notion of local causality in this model, because what I do over here can influence the state of affairs very far away, because the trajectory of the Bohmian position is part of the complete description of reality over here in this region, according to the model. Of course, we can't really hold this against the deBroglie-Bohm interpretation, because Bell's theorem showed us that every realist interpretation is going to have to fail local causality. And the deBroglie-Bohm interpretation just does it in a very explicit way, as we've seen here. Now, I should mention, actually, that the way I've just described it sort of gets things backwards. The history of the topic is that Bell was interested in hidden variable models. He knew about a lot of existing no-go theorems. So in von Neumann's textbook, he basically said you can't have a hidden variable model. And he was appealing, von Neumann was appealing to a kind of non-contextuality. There were some other proofs in the literature of no-go theorems. And then he read Bohm's paper from 1950. And the quote on the first slide from Bell was, "I saw the impossible done." So he knew that there were these no-go theorems. And yet, here was a hidden variable model that seemed to reproduce all the predictions of quantum theory. What was going on? So he started to understand that there were assumptions that went into the no-go theorems, things like the assumption of non-contextuality. And then he recognized that Bohm's model, I mean, Bohm recognized it as well, but Bell recognized very explicitly that Bohm's model was non-local. And he started to wonder whether every hidden variable model and every realist model of quantum theory would have to share that feature of Bohm's theory. And he found that yes, and that's how Bell's theorem was born. So it was by studying Bohm's theory that Bell was actually led to his theorem. Another interesting point is that if you look at the history of the deBroglie-Bohm interpretation, so it started, the reason it's called the deBroglie-Bohm interpretation is that de Broglie had a model that was ultimately rediscovered by Bohm and slightly generalized. But de Broglie was proposing this at the dawn of quantum theory. So, at the 1927 Solvay conference, people were disputing the interpretation of quantum mechanics, and de Broglie's picture of particles being guided by waves was being discussed just as much as the Copenhagen and alternative ideas about how you should interpret the formalism. So it's not as if there was this entrenched Copenhagen consensus, which then later was challenged by de Broglie. It was more that de Broglie, from the very beginning, had this sort of picture in mind, and ultimately, for various sociological factors, de Broglie's interpretation lost favor. In particular, Pauli made an objection, which at the time de Broglie didn't quite know how to respond to, and so people sort of didn't pay attention to it for a while until it was rediscovered by Bohm, and de Broglie then started becoming interested in it again. But anyways, if you're interested in the history, there's a nice textbook that was published a few years ago called Quantum Theory at the Crossroads, and it's all about the 1927 Solvay conference, and it has a nice history of de Broglie's thoughts in it. And what struck me when I read it was that this failure of locality, surprisingly, is something that it seems de Broglie never realized. So de Broglie constructed his theory in the following way. He said, imagine every particle has its own guiding wave. So you have n guiding waves living in physical space, guiding each particle. So totally local theory. And then he thought that this theory here, which involves this wave function over configuration space, was equivalent to his theory, his local theory with the n waves. It's just another way of writing it, which to his mind was more convenient because it was easier to solve. So instead of having coupled partial differential equations for all these waves, you just had the one differential equation. But that step was actually a mistake on his part. The two theories were not equivalent. They were only equivalent for product states. And for product quantum states, we do have locality. But for entangled quantum states, we don't. And so de Broglie, I think, didn't recognize properly that his theory did have this non-locality in general. And had he recognized it, he might not have suggested it, because de Broglie was actually very committed to locality. And he was alive when Bell's theorem came out, and he was famously one of the people who never believed Bell's theorem and thought that there were problems with it. But interestingly, Einstein at the same time was thinking along hidden variable models, because as we saw, Einstein liked the idea that the wave function was an incomplete description. And it seems that he struck upon the same sort of approach, but Einstein recognized that it was non-local. And at the very last minute before the Solvay conference, he withdrew his talk. He was going to speak about these models. And then he realized they were non-local, and he thought that that's unacceptable. And so he didn't speak at the Solvay conference for that reason. So anyways, it's interesting. And I think history would have been very different if de Broglie had recognized his mistake early on. All right. So finally, I just want to say something about how we can reproduce the operational predictions of quantum mechanics. Yes? 2 slides? This one?
Yes. So can we say then that this induces collapse?
Does this induce collapse? I'm going to talk about collapse of the wave function just now, so hold on to your question. So in the very beginning of the course, I said, well, we can formulate quantum mechanics operationally, and one of the advantages of doing so is that when we look at any given realist interpretation, we can always ask, does it at least reproduce the predictions of operational quantum mechanics? That's sort of a minimum requirement of empirical adequacy. So let's ask that question for the de Broglie interpretation. So imagine you're doing a measurement of some Hermitian operator A, which has eigenvectors phi k. And we're going to do the same kind of measurement interaction between system and probe that we've seen earlier, a kind of von Neumann interaction. So we start the probe off. So the probe's coordinate will be denoted r prime. We start it off in some wave function chi. And we choose the interactions such that for each different phi k, the eigenvectors of A, we evolve the probe to a different wave function chi k. And so we'd like these wave functions to be distinguishable in order for this to really, for the probe to really have learned information about the value of A on the system. Of course, if we start out in a coherent superposition of these phi k eigenvectors of A, then we evolve to this entangled state between the system and the probe. And that's where all the problems, the measurement problem, the Schrodinger cat stuff came in previously. So now, if you make the following assumption, that your apparatus is such that the different wave functions corresponding to different outcomes are not only orthogonal in Hilbert space, but they're also non-overlapping in configuration space. Okay? So if I have a physical pointer that actually points to the left or the right, depending on the outcome, then it's pretty clear that the wave functions corresponding pointing this way and this way will also be non-overlapping in space. And then if you ask, well, what's the probability density of finding Bohmian positions for the system and the probe in the support of just the jth wave in this decomposition? Well, that's just the mod squared of the jth branch, which is this. And then if I ask, well, what's the total probability of being in the jth wave? This is just the density. Well, I integrate over the region of configuration space corresponding to the jth wave. And in that region, these wave functions are normalized. And so it's just mod Cj squared. And so this says that the probability that the Bohmian configuration lands in the jth branch of this wave function is exactly what orthodox quantum theory tells me is the probability of getting the outcome corresponding to the jth branch. And then if you ask, well, how do the wave function of the system, how does the wave function of the system evolve after that? Well, because only one of these waves is occupied and the others are empty, the dynamics of that system depends only on the occupied wave. That's what we showed earlier. It doesn't depend on the empty waves at all. So if you ask, well, what's a convenient way of describing the dynamics of that particle? It's using just phi j, the wave function of the system, for the branch of the occupied wave. And so that's like an effective collapse. According to the deBroglie-Bohm interpretation, there are no collapses of the wave function. It always evolves according to the Schrodinger equation. But there are effective collapses in the sense that it's sufficient to use this wave function to figure out how the particle is going to move after this measurement is done, because all the other terms in this wave function become totally ineffective. They don't influence the dynamics because they're empty waves. So again, we see we have agreement with operational quantum mechanics because we've not only derived the right statistical probabilities, we've derived essentially the projection postulate, the notion that for the purposes of predicting the outcomes of future measurements, it's sufficient to use this wave function. But there's a concern here. There's something I haven't quite addressed that you might be worried about. Is anyone worried about something here? Should I stop now, or is there more I need to tell you to ensure that we really have reproduced the predictions of operational quantum mechanics? Yes?
So you're saying the Bohmian position of the particle will collapse to being only in the support of phi j?
Mm-hmm.
Could it in the future evolve to being support of some other component?
Exactly. Like what we saw on the last slide was a case where for a while the position of this particle depended only on one of the branches. But then, hey, we did something over here which made those branches overlap again, and now all of a sudden all those empty waves became effective. They started governing the position of this particle again. So how can we really say that we've got success here when, okay, for the moment it looks like all these empty waves are ineffective, but what if by virtue of future evolution these wave packets come to overlap again in configuration space? Then it would seem that we don't have irreversibility, and yet the operational approach to quantum theory says once the collapse is done, that's it. So what's the solution to this for the Bohmian? And what would that do? Yeah, decoherence is the way out. So you can make even this effective collapse effectively irreversible by appealing to the fact that real measurement devices tend to interact with their environments. So let me take you through that argument, and then I'll stop. So suppose that we have a number of other degrees of freedom, R prime, R triple prime, et cetera, lots of them, which constitute the environment of our probe or our apparatus. So in my example of a needle that goes one way or the other, there's all the air molecules in the room that bounce off that needle. There's all the photons that come in and have an image of where it was located. All those many, many degrees of freedom carry away information about whether the needle was here or here, which means that depending on chi k, the position of the needle, I get different states of that environment. And furthermore, in addition to all these external degrees of freedom, there are often microscopic degrees of freedom inside your apparatus, which carry away information about those coarse-grained properties that you're interested in. So it could be that whether the needle's here or here actually influences also some internal degrees of freedom of the needle. And that can also be incorporated here. OK, so if I start with a superposition of eigenstates of the system, well, then even the environment gets coupled into this large entangled state. And now the point is that generally what happens with real environments is that not only do the different environment states become orthogonal in Hilbert space, they also become disjoint, i.e. non-overlapping in configuration space. Like all the light particles that tell me where my pointer's pointing, they're going to be spatially configured differently depending on where the pointer was pointing. Or similarly with the air molecules that bounce off of it. So this is generally the case for real models. Then, again, we can postulate an effective collapse because only one of these waves can be occupied. Now the environment guarantees that they're all disjoint. But the real difference is that if we wanted to re-interfere the empty waves with the occupied wave, now we have a much harder task. Previously, when there was no environment, we just had to make sure that these different chi-k's, which are non-overlapping, sort of were made to evolve and overlap again. But now we have to take all the bits of the environment and make them overlap again. So if there are 10 to the 23 degrees of freedom in the environment that have interacted with your system, you would have to somehow get that all together, make it evolve in this very particular way such that those states no longer, by virtue of their spatial degrees of freedom, tell you, which outcome occurred in the measurement. And that's something that is practically extremely difficult, if not impossible. And so now you really do have an effective collapse of the wave function. And that's where I'm going to end today. We'll talk some more about deBroglie Bohm tomorrow.